Hello, my name is Sergio Gomez, and I will be doing the final project motor simulation presentation for EML3036. My team members are Joshua Fernandez and Kimberly Smith. Joshua Fernandez is a junior at FIU. He is studying mechanical engineering and computer science. He enjoys working on cars, drawing, digital design, modeling. Uh, his preferred class so far was mechanics and material science. He enjoys electronic dance music, and his favorite quote is, "It's never too late to be what you might have been." Kimberly Smith is also a junior at FIU studying mechanical engineering. She enjoys taking pictures of nature, helping people with their genealogy. Her favorite class thus far has been thermodynamics. Her favorite movie genre is sci-fi, historical dramas, and psychological thrillers. And she chose a quote from St. Francis of Assisi. As I said earlier, my name is Sergio Gomez. I'm also studying mechanical engineering. Graduate May of 2024. I enjoy working on cars, riding motorcycles, and cycling. Mechanical design was my favorite class thus far. I enjoy romantic comedies, dramas, and psychological thrillers. In terms of the actual project that we're presenting today, the goal is to expand upon the initial model we did earlier in the semester that went just through the motion analysis to actually start critiquing the mechanical properties and thermal properties of the design. In order to do this, we actually chose to make some base assumptions. Instead of looking at the system as a four-stroke, we went for a two-stroke for simplification purposes, even though we're not utilizing the actual head of the engine for these testing. The maximum crank speed was determined to be 13,000 RPM. The flame temperature is at 2,800 degrees Fahrenheit. The cylinder wall temperature is 375 degrees Fahrenheit. The ambient temperature within the system at cold is 293 degrees Kelvin. And the average piston face temperature is 575 degrees Fahrenheit. The maximum acceleration was found through our motion analysis and ended up being 64,757.127 meters per second squared. The piston mass was also calculated through the SolidWorks simulation of 478.97 grams. The maximum force was calculated by determining mass times acceleration, which ended up being 31,016.721 newtons. The dimensions for the engine are 52 millimeters for the stroke and a piston diameter of 70 millimeters. That gives us a cubic displacement of 200 cc's. And then we also found the heat transfer from piston to cylinder walls equivalent to 209,430.05 watts. And that was actually by using a Taylor correlation and then looking at the characteristic gas velocity, factoring in the RPM and the stroke to come to that analysis. That's all presented in the actual report. We're just going through the simulations here. These are all the separate sections that we will be covering: piston compression, piston pin shear, the connecting rod compression, bending, and buckling, the crankshaft bending, torsion, and then the pistons steady thermal and transient thermal from a cold start perspective. The settings for the piston compression are presented below, where we have the fixed interface between the piston and wrist pin. We also have the fixed horizontal movement of piston walls against cylinder walls, and they allow for vertical displacement. And then the applied force is on the top surfaces. The material is an aluminum alloy 4032T6 with a yield strength of 3.150 E to 0.8 pascals. The results are presented below. We ended up coming in with a minimum factor of safety of 6. Now, this is actually excessive, and we do recognize that the mass of the piston is significantly higher than a traditional configuration. Most of the examples we found online were somewhere in the neighborhood of 200 grams versus our 400 plus, which is what's leading to this high factor of safety. In an additional redesign, we would consider shaving additional material off the side of the skirts, but for simplification purposes, we decided to proceed with this model of the engine. Moving on to the piston pin shear, the settings actually had us put it in a double shear against the piston, where the rod was acting in the center, and then the force is applied vertically to the bottom face, as presented here. In terms of the material, we actually had to do an iterative process because at first we use an AISI 4131 steel that was annealed at 865 degrees Celsius. The strength has a yield strength of 4.6 e to the positive 8 pascals, but the stresses were significant. And what we ended up doing is we normalized a range of thicknesses between 2 and 6 millimeters with 0.5 increments. And we ultimately found AISI 4340 steel was the appropriate one with a 3 millimeter wall thickness. That ended up giving us a minimum factor of safety of 1.2, which is just above where we wanted to be. Ideally, we would have wanted to be closer to 2, but this does work for our application. Moving on to the compression. These are the settings for the compression of the connecting rod. The connecting rod material is 4340 steel that's also annealed. And if you look at the bottom of the wrist pin, its interface hole is fixed horizontally, and then the top surface of the crankshaft interface hole is fixed, and that's where we will be simulating the compression across those two sections. The results end up giving us a minimum factor of safety of 1.4, which is in line with where we wanted to be. Now, for the bending settings, we actually had to set the connecting rod to 15 degrees. That's the maximum angle, and that actually correlates to a downward piston force of 7,655.5 newtons. With those settings, we end up getting a minimum factor of safety of 4.5, which means this rod will not bend within our application. The next thing that we did was we went to the buckling settings, and we had to cut the cross section, and we did a cross section through SolidWorks and came out with 176.27 millimeters squared for the center section, where we are going to be doing the buckling analysis. The buckling analysis presented with a very high load factor of 45.157. There is no likelihood that this connecting rod will be buckling in our example. Moving on to the bending of the crankshaft, we chose a 4130 steel that was annealed at 865 degrees Celsius. You can see here where we went ahead and did our fixturing on the top face of the connecting rod bearing and the bottom face of the crankshaft bearing. We ended up with a minimum factor of safety of 3.4, which means that we are well in line with not having any limits within the design. We could potentially reduce material from the crankshaft to lower our factor of safety to increase responsiveness from the motor and have lower costs. Moving on to torsion, we ended up finding that the angle for the connecting rod of a 15.069 degrees was applicable here. So we applied that force in that direction. And then these were the fixturings that we did. With the torsion results, we end up with a factor of safety of 5.7, which means that we will not be dealing with torsion issues with our crankshaft. Moving on to the steady thermal analysis of the piston, we put in a temperature source of 1810.93 kelvins at the top face. And then we had a heat power load of 209 430.05 watts to the exterior surfaces. And then the results are presented here. We're not dealing with significant stresses from the heat application, and it's actually cooling relatively well going through the body of the material. The next section is the thermal cold start. In this case, it is a cold engine where we are doing an initial temperature analysis with it going through the cycles for the first second in 0.1 seconds with 10 time steps. We set the part to 293 degrees Kelvin, which is normal temperature, all throughout its phases. And then in the next screen, we actually present the actual steps. If you notice, within that second, there is no fluctuation in the temperature. It stays consistent throughout the entire body, which works very well for our application. In conclusion, we found that the system worked very well. There were some hindrances that we should consider for the next process if we were to actually proceed forward with designing this motor. The first one, dropping the actual mass of the piston, potentially also changing out the mass of the connecting rod and crankshaft, we could substantially save in our factor of safeties. The one area that we could improve on is changing material selection for the piston pin. That the factor of safety there is a little lower than what we initially wanted for, but it does work for this design. Thank you very much.